basically on the Tonks-Girardot gas. So Thierry already explained what the Tonks-Girardot gas is. So it's the hardcore limit of the Lieb-Liniger gas. So it's hardcore bosons. And I want to put it in a trap. So Thierry explained that for experimental reasons it's important to have a trap. And basically the main message of this lecture is that so conformal invariance helps to get a lot of nice results. For instance, finite temperature, finite size systems, and so on. And the message here is that it also helps in the case of a trapping potential, at least for the Tonks-Girardot gas. I will not talk about anything else today, but the Tonks-Girardot gas, so it will be very specific. So Thierry already described the experiments, but let me just emphasize, just me elaborate on one specific point. So let's give some experimental motivation. So what I want to talk about is trap expansions and momentum distribution. Trap expansions in 3D and momentum distribution. And momentum distribution. Distribution. As Thierry explained, dimensional systems can be realized in the three-dimensional world, basically thanks to quantum mechanics. Because if you imagine that you have a gas of cold atoms, for instance, or that you trap, so that we put them in some three-dimensional trapping potential. So we have three directions x, y, z. X, let's say x, y, and z. Say. So they're on some 3D potential. So let's say at the lowest order of approximation, let's say this is a harmonic potential in the three directions. And so we will have a 1D system if it's a very anisotropic trap. So if the longitudinal frequency, so x will be the longitudinal coordinate, and the y and z will be the transverse coordinate. So if the typical energy scale for the longitudinal direction is much smaller than the transverse energy. Yes, sorry. Question? And if the temperature is much smaller than this energy scale here, then what will happen will be that the transverse degree of freedom will be frozen. So the atoms will be in the ground state in the transverse direction, and so you can forget this degree of freedom, and then you really have a one-dimensional system. Okay, so that was also explained by Thierry. And now, so one thing that experimentalists like to do is to expand so suddenly release the trapping potential. So that's something they can do very easily. And they like to do because typically it gives them a larger resolution, because if it's not necessarily very easy to probe directly the gas in the trap. so measure the in situ density, for instance. So they like to expand because then the cloud gets bigger and it's easier to measure. So what happens if you have a very so a gas of atoms that is confined in the transverse directions, in the directions x, y, and z, and that is quite elongated along the x direction. So what happens is that because of the Heisenberg uncertainty principle, if the atoms are very confined in the transverse direction, they will typically have a very broad distribution of momenta, and that means that if you release them, then some of them will have very large momenta in the transverse direction, and typically they will go away from each other very quickly. And because they will be away from each other, they will not interact anymore. So basically this you can model as a free expansion in 3 dimensions. So you can model this as in a semi-classical picture. You can introduce a distribution of particles at position x, y, z with momenta px, py, pz. And this object will simply behave as this. So at time t, okay, so this at time t, because the atoms are essentially free, this will simply be this. Times t at time 0. Okay, so the distribution at time t is directly related to the distribution at time 0, simply because if a particle is found at some position here, then you know basically where it was. If a particle at time 0 is here and has a given velocity, then you know where it's going to be after time t. Okay? Yes, the argument is that, of course, initially they're interacting, so at time 0 they're interacting, but then since you expand in 3 dimensions, very quickly, so the momentum in the transverse direction is very large, and so very quickly they don't interact anymore, and so this is accepted to be a good description. Okay, and so this is called time of flight experiment. And so the point is that this allows you to get the momentum distribution, which is the n of k that Thierry was talking about. And so why is that? Well, because if you imagine that you forget about, so you trace over the 2 transverse directions. So you take pictures of your cloud after some time of flight. And you imagine that you integrate over so you take pictures from the side, and the only thing you're interested in is how many atoms are in the plane, in the xy plane, in the yz plane at some position x. So you integrate over coordinates x and y. So this gives you some object that is the longitudinal distribution, which depends on position and momentum px after integrating over y and z, and py and pz. This object here. So you just forget about the transverse directions. You're interested only in the longitudinal position. So the claim is that at very large time, this will give you the momentum distribution in the initial state. So basically, you plot this. So you plot of course, you don't have access directly to the distribution as a function of position and momentum at time t, but what you have access to is the density profiles at time t. So as you expand, the density profiles will look like this. So this is the density profile at so the density at position x and some given time t. So initially you have a density profile that looks like this, say, very narrow, and then it expands. So it will broaden like this, like this, like this, and so on as t increases. So of course the density just goes to 0 everywhere because the gas becomes more and more dilute. But if you rescale it, so if you just rescale this density profile by multiplying by t and looking at along and take x of the form q over m times t. Yes. So then, in the limit when t goes to infinity, so you rescale vertically and horizontally, so that this goes to a well-defined shape. And this well-defined shape, which you can measure, is precisely the momentum distribution in the cloud at time 0. And so this is simply basically because you are looking at how many particles arrive here at time t, and of course how many particles arrive here at time t is directly related to how many particles were in the cloud, which viewed from very far away is a point. So how many particles were in the cloud with the correct velocity such that it arrived there. Okay? Should I be more... Should I enter this in more details? Okay, I tried to explain this properly in the notes. So the point is that this is related to some interesting correlation functions. That's the main message. Because as Thierry already said, the momentum distribution is related to an interesting correlation function in the Luttinger liquid, which decays with some power law that is fixed by the Luttinger parameter. And so this gives something that is worth looking into. Okay, so how do you calculate what is the momentum distribution? So to calculate the momentum distribution, you should look at, you want to calculate the expectation value of psi dagger q psi q. Okay, so this is 1, 2 correlation functions. So in the initial state, in the state at time t equals 0, I want to know, which might be a pure state or some thermal state. At this point, it doesn't matter. Just I have some state, and I want to know the momentum distribution. So the momentum distribution is this, because this is the Fourier transform of the operator that creates a particle at point x. I get a double integral that looks like this. So this is a q. This is q. Okay, and I can rewrite this as integral over x of dy e to the I qy psi dagger x plus y over 2 psi x minus y over 2. So this now I can identify, if you want, sorry, not this, but this thing here I can identify with my W3D longitudinal of x and q. So this object here is Basically, semi-classically at least, it's the probability of finding a boson at position x that has momentum q. So I call it W because it's called the Wigner function. And I'm not going to talk too much about the Wigner function in 3D. So the Wigner functions of the bosons, but I just want to introduce the object because it's going to be important later. The point here is that to calculate the moment, okay, so this is n of q in Thierry's notation, nq. And the point is to calculate this, you need to be able to calculate this correlation function in the state at time t equals 0. And this is, okay, so in the literature, this is often called the one particle density matrix. Density matrix. And so Thierry explained that this, in the homogeneous case or the translation invariant system, this follows easily rather easily once you have understood that the system is described by the Luttinger liquid approach, and then it just decays as the distance between the 2 points to the exponent 1 over 2k. But yeah. Yes, so that comes next. Thanks. So indeed, when you do when experimentalists do the measurements, what they do, it's quantum mechanics, right? So they prepare a cloud, they expand, they take a picture. The picture destroys the experiment. They start over, and so they again produce a cloud, expand, measure, and so on. So they do that hundreds of times. And they have access to the full distribution. So indeed, they don't have access only to this, but they have access to actually any, well, depends on how much statistics they have, of course, but in principle, they have access to correlation to higher moments of the momentum distribution. So things like this, for instance. And to calculate things like this, you need not the one particle density matrix, but the n particle density matrix. So you need the which now depends on many positions. And so on, and here, yeah, okay, anyway, so like this, right? So it's a 2 endpoint function. So there are 2 endpoint function. Okay, and again in the translation invariant case, you could just this is again a correlation functions of some of these exponentials of a bosonic field, and so you can calculate them very easily using Wick's theorem, and this gives you some formula, which again involves the Luttinger parameter. Okay, and this was explained by Thierry. But my main point is to explain how to do this in the trap, again, just for Tonks shadow. So at this point, I just wanted to show you that there are actually some experiments that do that. Thanks. I think, yeah. Okay, so this is another. Thierry showed one experiment. This is another where they really. This is really the quantity they were investigating. So the first. They were really investigating this. So the first correlation. So the first moment of the momentum distribution. So what you should see here is the vertical axis is Q1, the horizontal axis is Q2 if you want, and they're really calculating the connected part of this. So the connected part of this correlation, and so the top is the experimental data for different values of the repulsion strength in the gas. And the middle row is the theory that was obtained by Quantum Monte Carlo, and as you see, it works quite well. And so the theory was done with the Liebling model at finite temperature. So this is rather high temperature. It's like the Schmid-Meyer experiment that Thierry was showed. So it's rather large temperature, and very small repulsion strength. So it's very, very far from the regime I'm going to focus on, which will be zero temperature at extremely strong repulsion. But still, this is just to show that it's the kind of quantities that are relevant for experiments. Okay. All right. And let me emphasize also something else that Thierry also said already, but let me just stress it again. So it's long range aspects versus short range. Mm-hmm. This is the number of both by expanding in 3D and looking at the position, the positions of the particles after a very long time of flight along the x-axis. Yes. Yeah. So you see the 2-point function enters here. The 2-point function enters here. You calculate its Fourier transform. It gives you this object. You integrate over x. It gives you this n of q. So if you have the 2-point function, then it's just a matter of evaluating this integral. So maybe you don't have a closed formula for the integral directly, but I mean this is kind of not the interesting step. The interesting step is to get the correlation function. Mm-hmm. Other questions? Okay, so as Thierry emphasized, everything that you get from the Luttinger liquid approach is about long-range physics. So low energy physics. So it's about the behavior of correlation functions at long distance in real space. And so because it's long distance in real space, it tells you something about the small k behavior, so a small q behavior of the momentum distribution. But what it does not tell you is about the large q behavior of the momentum distribution. So the large q behavior is not described, by Lottinger liquid physics. Not described by Lottinger liquid. So that doesn't mean it's not interesting. There are still interesting things to say about the large Q behavior. In particular, actually, I don't know. Maybe some of you know this. There's something called the contact. That so many people are working on this. So again, let me just emphasize this contact has nothing to do with Lottinger liquids, just to avoid confusion. So what is this? So basically, what you can show is that this function G1, so the one particle density matrix, it's a continuous function at x equals x. So it's continuous at x equals x prime. Sorry. It's continuous. The first derivative is continuous. The second derivative is continuous, but the third derivative is not continuous. And consequently, when you calculate the Fourier transform of this object, because the third derivative has a discontinuity, so when you calculate this, which is the object that enters here, this will automatically behave as some constant that depends on x, divided by, sorry, that's the Fourier transform, so it's e to the iqy. So this will automatically have a decay as 1 over q to the 4 when q is large. And this factor that appears here, this coefficient c, this is called the contact or Tan's contact in the literature. And I just wanted to mention this because there are many papers on this. And again, Lottinger liquid physics doesn't tell us anything about this. This is entirely about short-range physics. So it's basically, if you want to learn about this, you have to calculate one-point functions, so the correlation functions of something local. And this, you need really to know about the macroscopic model. So it's more like Bethe-Ansatz type of calculation. And this is not what we're going to do today. So what we are going to do is about the long-range physics. Again, it's Lottinger liquid. And we want to learn how to do this in the trap. Okay, any questions so far? No? Okay, so let me briefly revisit what Thierry said about the hardcore limit. Okay, so the Tonks-Girardot or hardcore limit. Okay, so I'm gonna say exactly what Thierry said, just in a different word. So I just quickly want to introduce Jordan Wigner. So the Jordan Wigner string. So that was also mentioned by Bruno, and he gave that as an exercise, if I remember correctly. Okay, so this also works in the continuum. So basically, we are interested in the Lieb-Liniger Hamiltonian. So recall that it was like that. This plus g over 2 psi dagger squared psi squared, and we want to take the infinite repulsion limit, so g goes to plus infinity. So because g goes to plus infinity, the bosons become hardcore, and so you can think of them as fermions, except that they don't have the correct statistics. And so to correct the statistics, You can introduce fermion, so fermionic operators that look like this. So this is the operator that creates a boson. This is the operator that creates a fermion. And in order to get the correct statistics, you need to insert this object here, which is a non-local operator, which is basically -1 to the number of particles, that are on the left of the point X. Okay. So is everybody? I mean, do you all know about Jordan Wigner? Okay. So if everybody knows about Jordan Wigner, I won't say more about this. So as Thierry said again, the Jordan Wigner string is really a pain if you want to calculate, for instance, correlation functions of the bosonic. Yes. You don't know about Jordan Wigner? Well, then I would refer to your book, right? You know? Okay. Well, so the way I would quickly explain it is just say, let's pretend that we want to. Okay, so let's just check that we have the correct anti-commutation relations at different points. So let's not focus on same points. So I take x different from x prime, and I just want to check that I go from the commutation relation, say from psi dagger and psi, that this transfers to this because anti-commutator because of the string. Okay, and so I mean, sorry, thanks. Yes. Okay, so that you can view with a picture. So imagine that x is on the okay. Let's imagine we have some state psi, and we first act with psi at x prime. So we want to destroy a boson at position x prime. This is x prime. And let's say that x is smaller than x prime. So then and then I create a particle at position x here. So if I look at, okay, so this is one drawing, this is time. Okay, so first I take the state, I apply an operator here, and then after some small time, I apply another operator here. This is the same thing, because they commute, it's the same thing as doing it the other way around. Yes, sorry, so psi dagger of x, psi of x prime. Okay, because they commute. Now, if you add the string, so now instead of acting with psi dagger, I act with psi with the string. So I'm adding the string here, which puts a minus sign. So -1 times the number of fermions that are here. You see that now there's a minus sign. There's a minus sign that shows up when I do this, because here I have added a particle, and so I pick this string here picks up an additional minus sign, so it puts the minus here. So this now is equal to minus this, and this is the reason why it becomes an anti-commutation relation. Okay. Any questions? Okay. Okay. So this is. I mean, this is simple, but you have to. I mean, you have to learn it. I mean, for the first time, it's non-trivial, but then it's fairly easy. Good. So now, okay. So as Thierry said this morning, the fact that the hardcore limit maps to free fermions helps calculating a lot of things, and in particular in the language in the language that I was using on Monday, it helps calculating the equation of state. So 2 is the equation of state. Equation of state of the Tonks-Girardot gas. Okay, Tonks-Girardot gas. Or of the free fermion gas, because it's as long as local correlations are concerned, it's the same thing. In particular, the density of bosons is the same as the density of fermions. Why? Simply because the density is a quadratic operator in psi diagram psi, and so if you write it, the Jordan-Wigner string cancels. Okay, so it maps to a gas of free fermions, and because it maps to a gas of free fermions, the ground state is a Fermi C. So the ground state of the gas at a given density satisfies these constraints. So if I try to create a fermion that has momentum q, and the momentum q is smaller than the Fermi momentum, then this doesn't work because it's a fermionic state that is already filled. So this is 0. And if I try to annihilate a fermion that has a momentum larger than the Fermi momentum, then this is also 0. Okay? So that's the ground state, and then you can calculate the density just using this and the anti-commutation, the canonical anti-commutation of the fermions, which reads as this. This is delta x minus x prime. So using this and this, you can easily calculate the density in the ground state. So the density in the ground state is, just let me. Okay, so on Monday I was using the mass density, and so okay, I'm using notation so that this is the mass density, not the particle density. So of course it's the particle density times m, but okay, this is why I have m's everywhere. So this is just Fermi momentum divided by pi times h bar. Okay, so this is the density as a function of the Fermi momentum, and by a similar calculation, there's something crucial that I forgot to say. Sorry. Yeah, of course, this was the most important part. Okay, so the most important part was that this Hamiltonian, once you rewrite it in terms of the fermion and creation annihilation operators, this becomes a quadratic Hamiltonian. So this is psi dagger f minus h bar squared over 2m t plus v psi dx and this is psi f, and there's nothing here. So that plus, so there is no interaction term here, which is different from this. Right? So it's really a free fermion Hamiltonian, and so this is why it can be solved in such a simple way. Okay, so by calculating the expectation value of H in the ground state, you can also get the energy density in the same notations as I was using on Monday, and this is now. So this I can also express in terms of the Fermi momentum. Okay, this is not so important. So let me just so up to some coefficient, it's the Fermi momentum to the power 3, and then what's important is that we get the equation of state. So equation of state for that is obtained by taking v equals 0, so obtained in the homogeneous system, and so this is it relates the energy density to the particle density in the following way. So it's this. Okay. I mean the prefactors obviously are not so important. What's important is that we have a relation between the energy density and the mass density. Okay, and using the formulas I gave on Monday, let me just rewrite it. This gives us the pressure of the Mussardo gas as a function of the density, and this is what we need to do hydrodynamics at 0 temperature. Okay, so I said on Monday that the pressure was minus rho E plus rho D rho E divided by rho. This is true at 0 temperature. 0 temperature. And okay, so in that case, you can just plugging this in there, you find that the pressure is pi squared h bar squared rho to the 3 divided by 3 m to the 4. Okay? And so now we are ready to do hydrodynamics or hydrostatics or whatever. And in particular, we can easily now get the density profile of the gas in a trap. So now we switch on V, and we want to look at the density profile of the gas in the trap, using, again, relying on the hydrodynamic approach, so relying on the idea of separation of scales. So we are assuming now that we have a potential that is varying sufficiently slowly at the interparticle distance, and we want to calculate the density profile of the gas at 0 temperature in that potential. So any questions so far? No? Okay. If I'm going too slow, just tell me. I can go faster. Yes, okay, so now we are really going to focus on the trap. And okay, so hydrostatic profile, or if you prefer, local density approximate, the profile that is given by the local density approximation. It's really this local density approximation is just another name for hydrostatic. Okay, so we saw that we had these Euler equations. Okay, with the pressure that is now given by this. And so by doing hydrostatic, so if we do hydrostatic, we're looking for a solution where the mean velocity of the fluid is 0. So so this equation now is trivial. If we do hydrostatic, this term vanishes, and we end up with this. This is the condition that we have for hydrostatics. Yes. Yes. So U. Yes. So thank you. So U was J over rho in the density current notations. Yeah. Mm-hmm. Yeah. So we are looking at a situation where the fluid is where the gas is locally at equilibrium, not moving, not doing anything. And so we set U equals 0.
So I thought this form had did it rely on Galilei variables?
Yes.
So the Libanian model is not by this Galilei.
Yes. Yes. Sure. Yeah. Mm-hmm. Yeah. It is Galilean invariant because. Yeah, because the interaction term is of the form V x1 minus x2, if you have two particles at x1 minus x2. Mm-hmm. Any other questions? Okay, so let me just finish this and then we can take the break. So, all right. So I won't solve this for you. You can do it as an exercise. But the answer is very easy. So the hydrostatic profile reads like this. So you will find, if you look for the solution here, you will find that this goes as. Okay, so again, I have some annoying factors of m because I'm talking about the mass density. But anyway, later I will set m to 1. So you will find that the solution is of this form, where mu mu is an adjustable parameter. So because there are different solutions, there are several solutions, and which are parameterized by mu. So mu is a parameter that you can adjust, which is of course nothing but the chemical potential. So that it's a free parameter if you want, which is the chemical potential. And of course you should fix the chemical potential so that the total number of particles is the one you want in your system. So mu should be fixed such that you recover the correct number of particles. Should be fixed such that this is true. And so okay, so let me just emphasize one point. So of course at this point everything is relying on a hydrodynamic approach. So we are again relying on separation of scales. And so just to be sure that what we are doing is not complete nonsense, let's just check that indeed separation of scales is satisfied if we have a solution of this form. Okay, so I personally, okay, so that you can work in the units you like, but so personally, I like to work with the following units. So I like to set m equals 1, chemical potential also equals to 1. And so if V is harmonic, so because V varies, so there is a typical scale on which V varies, and this allows you to define a length scale. So just for the sake of this argument, let me take V harmonic. And then I can set omega to 1, say. So this fixes the time scale. This fixes the time unit, energy unit, and this fixes then the length unit, if you want. And so in these units, we can take h bar to 0, and you see that taking h bar to 0 in the formula for the density here is the same as taking the density to infinity, or if you prefer, the total number of particles in the system to infinity. And then you can easily check that the macroscopic scale, which is the scale on which the density varies, so which is a form of d rho over d rho. So in these units, this is of order 1. The density itself is of order h bar. So this is much smaller than this, and then you can always find some mesoscopic scale, which is of order, you can take whatever, for instance, anything that is of order root h bar or whatever. So yeah, this is just fixed some conventions. So we are interested in the limit where n goes to infinity, or h bar goes to 0, keeping these parameters fixed. So this will somehow fix the geometry of the problem, and then we just sort of send the density of particles at every point to infinity, so that the microscopic model, which is really a gas made of particles, really becomes a continuous object.
So we neglected V in the Hamiltonian, and then we got the V in an equation of state, actually, which we assume doesn't change then when V is turned on.
Yes, exactly. So the equation of state is derived in the homogeneous problem by definition. So assuming that we have separation of scales, we know that we can replace the local pieces of fluid by a locally homogeneous problem, and use the equation of state derived in the translation invariant problem as an input to solve the problem in the trap. Okay. And of course, this is always, everything here is relying on this assumption. If this is not satisfied, then everything goes out of the window. But this is just doing, this is what it means to do hydrodynamics. Okay? So before we take the break, let me just tell you what I'm going to do after the break. So my point now is to write some correlation functions of the gas in the trap, in the ground state of the in the trap, and in particular, I want to focus on the one particle density matrix and derive this nice formula. So A is the same constant, I think the same constant as the one that Thierry was talking about. Not completely sure we have the same notations, but I think so. And then, okay, so it will scale like the local density at point x to the 1/4, and x minus x prime to the 1/2. So that what is amazing here is that it's so simple in the end, and this is for the harmonic trap. So notice that at short distance, if x is very close to x prime, then you recover what Thierry said. So this just goes as this non-universal, this amplitude here, this numerical coefficient, times root of rho 0, which is called the rho 0 in his lecture, and 1 over distance to the 1/2. In his lecture, where he was taking an arbitrary Luttinger parameter, in more general, this was 1 over 2k. And here, of course, since I have free fermions, as he said, and as we said also last week, we actually have k equals 1. So that I'm going to rederive after the break, so don't worry. My point here is just that at short distance, this reproduces the behavior from Thierry's lecture, and it's just that you can actually get it in the trap also. So then you have, in that case, at least the trap is not such a big annoyance, because you can actually you can actually take the results from the translation invariant case, and thanks to conformal invariance, convert them into results in the presence of the trap. And actually, this generalizes also to the n particle density matrix. So let's and the generalization is very simple. So let me just write it. So it looks like this in the end. So it's a product of all the rows at position xy, x4, products. So this is from 1 to n, j from 1 to n, row node of xj, 1/4 divided by time. Okay, and then we get some factor that really looks like this Cauchy determinant formula that I was talking about last week, except that there are some powers 1/2. Yes, so this x prime x1 p1 minus x prime p2, also to the power 1/2 divided by product of p and q of xp minus xq to the 1/2. Okay, so you can derive formulas like this, which look very much like the translation invariant case, but you can also do it in the trap. And this is again thanks to conformal invariance. And so I'm going to use the machinery we developed last week in the tutorial to derive these equations.
Sorry, is this effectively then the local density approximation allowed by the separation of scales?
Yes. So what's
Is this called the local density approximation, or is just like as if you're finding the density?
Yes. I mean, yes, if you want, yes. So the local density approximation is precisely relying on this assumption of separation of scales. In that sense, it's the same thing. Okay, so I think we can stop there. Hello? No. Okay. All right. All right. So Okay, so now we are going back to the Luttinger liquid, and so to describe the quantum fluctuations around this profile that I erased. But anyway, so around this classical background profile rho naught of x, which describes the density in the ground state. So this is the density in the ground state, in the trap, in the ground state, in the trap. And again, in the local density approximation, or hydrostatic, if you want. So the underlying assumption is always that there is this separation of scales, or hydrostatic. Okay. All right. So we would like to be able to calculate correlation functions in the ground state. So by the way, this is 3, 2, I think. So ground state correlations. Ground state correlations. Okay, so we would like to be able to calculate correlation functions like this of some observables at different points. And so it's a useful trick to think of this as being the zero temperature limit of a finite temperature correlation function. Okay, so these are beta h, where h now is the Hamiltonian with the potential. Hamiltonian with the potential, with V of x. And we put a chemical potential. Okay, does it? Yes. No. So we can put O1, ON. Mm-hmm. Mm-hmm. Let me erase this. So is this clear to everybody, or should I explain this? So what this does is that, so why is this true? Because the ground state, this state here is the ground state of H at with some chemical potential, so that I'm correctly adjusting the number of particles. So this state here is the ground state of this of this operator here, and so then taking this exponential of minus this beta times this operator, taking beta very large, does project onto the ground state of this. Okay, and so then I recover this, and I need to properly normalize things, because otherwise I would get the largest eigenvalue, smallest eigenvalue of this well, basically I would just get e to the minus beta times the ground state energy, and this I need to cancel this factor. This is done by this. Okay. All right. So this is just a particular way of representing ground state correlations. But when we go towards field theory, it's useful to think of it that way, because then we start seeing the geometry of the problem. So now let me again coarse grain the problem. So at this point, this was true in the microscopic model, but now I want to coarse grain, and so I want to go to these variables that parameterize our system at the mesoscopic scale. So I want to go to to continuous fields rho of x and tau, and tau will be the time or imaginary time, and u of x and tau. Okay, why does imaginary time come in? It's because this exponential of something times a Hamiltonian looks a bit like an evolution operator, but there's no I there, so it's like an evolution operator in imaginary time. All right, so when we coarse grain, then these correlation functions here start looking like this. So again, this is ground state correlation of some observables. So now it's the limit when beta goes to infinity. Okay, so again, let me formally write this as we did last time. So I want to integrate over rho and j if you want. So u is j over rho, over all possible configurations of the density and the current, but I want the density and the current to be constrained by the continuity equation, which looks like this, times the operators times exponential minus the energy, essentially. So energy of rho and j, total energy. So energy integrated over time. So let me call this S. SE maybe. And again, the denominator is just here to have the correct normalization. And so this coarse-grained picture, again, I would like to emphasize that it's correct. It becomes correct in the limit where h bar goes to 0, or if you want number of particles goes to infinity, keeping everything else fixed. So keeping v of x the potential fixed, keeping chemical potential fixed, mass fixed, the positions fixed, and everything. Okay. All right. So now I need to tell you what this. This is basically the energy integrated over time, or if you prefer, it's the Euclidean action. So this we can write as this. And last time I just said I took a completely generic form of the action, but now I really want to use the correct one, and the correct one is this. Okay, so v minus v of x minus mu. V of x minus mu times rho. Okay, so that's this is the potential energy of the particles in the trap. This is the internal energy, so it's the energy density at a given density, so due to the interactions between the particles, and this is the kinetic energy. And sorry, and my notations are that, okay, so we have the my notations are the following. So we have a potential V of x that does something like this. Say we have a chemical potential that is here somewhere, and so the system will be filled in an interval, in a finite interval, which is the region where the potential is lower than the chemical potential. So where mu minus v is positive. Okay, and this finite interval I will call. I mean, this I will assume that it's x equals 0, and this is x equal L. Okay, so the interval 0 L will always be the interval that it will be filled with particles. Okay, and this is this 0 L that shows up here. Any questions so far? No? Or yes. 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 So you're worried that it can be negative, or what? Yes, but then we will expand to second order around this, right? So yeah. Mm-hmm. Yes. Okay. So that's right. So in principle, there should be an additional constraint that rho should be positive and so on, because otherwise this is not really a physical configuration. But of course, what we are going to do is just expand, consider small fluctuations around the classical solution, which is this one, and so then there will be no problems. Okay. All right. Okay, so let's let's go through what we did on Monday once again. This time in this context. In this context of this Euclidean action, now with this, so the difference with what we said on Monday, with what I said on Monday, was that there was a minus here. There should have been a minus because we were doing things in real time. But okay, now now everything is Euclidean. Okay, so we go to so now we say S of E of some configuration rho and J. So we want to take rho as a small perturbation around the hydrostatic classical solution. So rho plus delta rho, and J. Okay, J should also be a small perturbation, but since J is U over rho, and we are looking at fluctuations around the static profile, U is just 0, and so this is delta J, but this is 0 here. This is just 0. Okay, so J is some small, so 0 plus delta J. Okay. All right. So, okay. So let me just write the result. So now we plus delta rho, delta J. So this is SE of. So there's a constant part, which is the energy of the classical solution plus the energy integrated over time. Yes, and then I take, okay, so here I take the limit beta goes to infinity, so that now I have replaced this by an integral from minus infinity to plus infinity. Okay, this is this limit here. All right, and so this is okay, so again, the first order vanishes automatically because we are assuming that rho naught is a solution of the classical equation, and then we end up with this. Delta rho squared. I mean, the specific form is not so important. Again, what's important is the same thing as last time, which is that this is a quadratic action. So again, the argument is that in principle there should be also higher order corrections, but those are irrelevant in the renormalization group sense, and so we just neglect them. Yes, and okay, and so that what's important is that we arrive. Okay, so I won't do it in detail, but we are then again. So we like last time, we now have this delta rho of x and tau. This we take as 1 over 2 pi derivative with respect to x of h, and delta j we take as minus 1 over 2 pi derivative with respect to tau of h, so that this is chosen so that the continuity equation is automatically satisfied. So okay, so dt delta rho plus d tau delta rho plus dx delta j is 0. And so then we can replace the path integral over rho and j by an integral over this field h. And so we get an action for h, which represents the fluctuations around the classical solution, which you can put in this form. Sorry, this is... Yeah, which we can put in this form. Where this G, so G is a 2 by 2 matrix, which you may view as a metric if you want. It's useful to look at it as a metric. It's just superfluous complication. It's really useful to look at it as a metric because then it will tell us exactly what we need to do. So this is the okay. So this metric takes the following form. So because we are in the, notice that there is no term dx d tau, which means that G is a 2 by 2 matrix that is diagonal, and this is because we are in the ground state, and in the ground state the fluid has no current, so locally it looks like it's time reversal invariant, or if you prefer parity invariant, and so this kills this kills any term that would be of the form dx d tau. And so because this term is not there, then there are two parameters, only two parameters left in our quadratic action. That's k and the local k, so Luttinger parameter k, and the velocity of sound velocity, v, which now depends on x because we are in a problem that is not homogeneous. So yes, so let me just give you v and k. So v and k can both be derived from the equation of state. From this. So in particular, the sound velocity. So the sound velocity turns out to be root of rho, second derivative of rho e with respect to rho. So in terms of the density, so the velocity of sound is directly proportional to the density. For the again, this is true for the Mussardo gas. This is v, the velocity, not sound velocity. Sound velocity. It's not the potential. No, it's not. There are two different things in so it's a one-dimensional gas. There are two different things. There's the mean velocity of all the particles that you have in the gas. So you look at your gas, all the particles are moving around. You take their average velocity, and that's what U is. V is not the same thing. So the V is like if you take your gas at equilibrium and you kick it, so you kick it somewhere, then it's gonna generate an excitation, which is part of it is going to propagate to the right, part of it is going to propagate with to the left. So it's gonna generate a sound wave that's going to go through the system, and V is the velocity of this sound wave. No.
Is there a bit more general, like, because there's still a sense of propagation of excitation, or like, do they have at least a physical connection?
There is a connection, but it's not simple, so I would rather not talk about it. Yes, maybe I'll try to talk about this on Friday. Yes. Between the rapidities and the sound velocity. Okay, at a naive level, they're related in the sense that the sound velocity can be calculated from the Bethe-Ansatz solution, and the rapidity, of course, enter the Bethe-Ansatz solution. Now, if you want to be more precise, you have to enter really a discussion about the Bethe-Ansatz, and I'm not going to do this today. Yes, questions? No? Yes, and K is 1. K is 1, thanks. So, yeah. So you can derive it directly from here, you see. I mean, you just put the right coefficients, and you can calculate K directly from the second derivative of rho, which is given by the equation of state. So you can really check that K is 1. But Thierry, of course, also explained this. So he explained it through correlation functions. This is also consistent with what we said last week. So we said last week that correlation functions of bosons have to do with correlations of functions of fermions if K is 1. So this is all consistent. So because the Tonks-Girardot gas maps to free fermions, we should expect to see something that is intimately tied to free fermions in the end, and this is where it shows up in the value. It fixes the fact we have underlying free fermions, fixes the value of the Luttinger parameter to 1. Okay. All right. So now, why did I write things in this fancy metric, in this fancy way? It's because now let me keep this. Okay. Well, problem is that I need everything. Okay, let me erase this maybe. Yeah. So okay. So we have now an effective effective field theory, which is just a Gaussian free field at k equals 1. In this metric where the sound velocity enters, and the problem that is caused by the trap is that the sound velocity now depends on the density through here, and since the density changes, the sound velocity changes. But because we have written things in this covariant form, we are free to choose to pick different coordinates in which the problem looks simpler. And so for this particular problem, there is a simpler choice of coordinates. So let me call it, let me write it as xi. I can introduce a new coordinate xi, which is going to be the integral from 0, so left boundary of the system, to a point x of d. Let's call this ds over v of s, where v is the sound velocity. So what this is that if you have let's say okay, so you have a coordinate x and t, and you emit a signal, say from here, from the origin, and the signal is moving at some velocity which depends on position. So the velocity here is like this. So the velocity is the inverse of that slope here. So this angle here. Sorry. But you can just, you can just locally stretch your coordinate x, or if you prefer, just measure things in terms of the time that is needed to go from the left boundary to here. So this is the time that is needed by a signal moving locally at velocity vx to go from 0 to x. So if you reparameterize things as in terms of that locally rescaled coordinate, then it just looks flat. So in terms of xi and t, this looks like a straight line. And so in terms of this coordinate x, this metric here now looks like v of x squared d tau squared plus d xi squared. And because we have the action in this form here, you see that we can always rescale the 2x2 matrix G. Root G is the root of the determinant of G. So if we just rescale G by a global scaling factor, it cancels with this one, and so it doesn't change anything, which means that we can just forget this. We can just rescale we can just rescale G by some factor lambda, So in that case, just by 1 over v squared, so that this so that we get rid of this, and the action doesn't change. So in these coordinates, we are really back at the Gaussian free field as we saw it last week. And so now just to summarize everything, we have arrived at the following thing. So we have arrived at this. So this is now okay. So this is now path integral over h of my operators O, x1, O, xn, e to the minus se of h now, which is my quadratic action. So let me write it as this, integral d2, okay, now I write it in coordinates psi and tau over 8 pi. Gradient h squared. Okay, where H is a field that lives in the following domain. So this now is time, or imaginary time, so it's tau. This direction is my coordinate psi. This is tau equals 0. So, and the ground state correlation functions that we are interested in are here. So the operators that we are whose expectation value we want to evaluate are living here. This is O. This is first observable, second, and so on. Okay? Now we have our field H, which lives in this domain, so in this infinite strip. From here, let me call this 0 and lambda, say. Lambda is integral for 0 to L of ds over vs. So it's in these stretched with using this stretched distances. It's the system size. And these O's now depend on psi. So this is again the fact that we end up with an infinite strip like this is really again this rewriting of ground state correlations as things at finite temperature, taking the limit of 0 temperature, because you have to imagine that you take some state here that it's periodic at infinity if you want. So if we were calculating things at finite temperature, then taking the trace in the path integral language would be like putting periodic boundary conditions in imaginary time. And since we are looking at 0 temperature, the boundary conditions go to infinity somehow. So this is space. The horizontal direction is space. And the vertical direction is imaginary time. And so this is what we have to calculate now. So we end up with our Gaussian free field, which is very simple theory, which we solved in the tutorial last week. And we have some correlation function of some observables on the strip. And I explained you last week how to calculate things on the strip. So basically at this point, the only thing we need to do is identify the correct O's. So the correct operators here. And this now connects to the lecture of Thierry. So any questions? Did I kill everybody? Yes. And, because in the way you write the action, you have the G with indices up, which is the inverse of the matrix G. But then you have the square root of the determinant of G. And so if you multiply G by a factor, then this is invariant. Right? Because this scales as 1 over lambda. Determinant of G would scale as lambda squared, but then the square root and so on. So, yeah. This is one way of looking. This is one way of seeing that this action here is conformally invariant. All right. So I won't. Okay, I won't say much more than this, but I want to discuss quickly the identifications of operators in the microscopic model with the ones in this effective field theory, because this is really a crucial point, and so this was also discussed by Thierry. But okay, so from this perspective, what's important is that is to say the following thing. So basically any local operator in this is some local operator in the microscopic model. So any local operator in the microscopic model you should be able to identify with an infinite sum of some local operators in the field theory. So this is an operator in the field theory. This is an operator in the microscopic model. So these local operators in the microscopic model, in terms of the tutorial of last week, these will be these operators V, P, Q that we discussed, and all their derivatives in the language of in the notations of Thierry. These are the higher Fourier modes of the operators, which involve these exponentials of phi times some coefficient. Let me call it a tilde of O phi. And basically everything, any operator can appear here on the right hand side. So any operator, any local operator in the field theory could appear on the right hand side, at least as long as it has the correct quantum numbers. So in particular, since we are for this one particle density matrix or n particle density matrix, since we are interested in the operator that creates a particle, these operators here should have the correct charge. Okay, and it turns out that the ones that have the charge are the ones here with Q equals 1. So for psi dagger, it's the ones that have Q equals 1, and for the psi's, it's the ones with Q equals -1. The reason is the following. So the reason is because the density is 1 over 2 pi times the derivative of of the gradient of h, so times the gradient of h. This is the fluctuation of the density, and the current is the derivative of this with respect to time. So here there is no current at the boundary of the domain. There cannot be any current. So the current here has to be 0, has to vanish, because it's just the edge of the cloud. So there are no atoms coming in or out. And so this means that d tau h has to vanish, because d tau is the current. So in other words, h has to be constant along this line. It also has to be constant along here. So in other words, we have Dirichlet boundary conditions. But now, if and so h fluctuates, so we have fluctuations of h, but it comes since h is the fluctuations around the background solution. The integral of h from one boundary to another has to vanish, just because the integral of h from one boundary to another counts the number of particles minus the number of particles in the ground state, and since we are in the ground state, this has to be 0. But now if we insert an operator here that creates a particle, then and we calculate the integral of h from here to here, this now is the number of particles after we have applied psi dagger minus the number of particles in the ground state, and so this has to be 1. And so this means that when we look at the variation of h around this operator, it has to jump by 2 pi. And so this is precisely what these operators we discussed last week do. So if we have an integer q here, these operators jump by 2 pi times q. In Thierry's language, these again are these exponentials of phi. All right. So, but as soon as they have the correct the correct charge, so the correct as soon as all these operators are really operators around which h has the correct winding, then anything can appear. And what's important is to know these coefficients. And these coefficients are known for the Tonks-Girardot gas, thanks to results from the mathematics literature from the I'm not going to start entering the calculations in any details. Let me just finish with this. So once you have identified the correct operators that appear here, and operator has a scaling dimension, let's call it delta j. This operator also has some dimension, and so this must scale as this has some length scale built in. But the length scale you can take out by saying that this has to scale like the local density to some power. So if this, to some power, which happens to be delta j minus the scaling dimension of this operator O. So this A tilde is equal to something that has to scale like this times a pure number. Sorry? Like this? Okay, thanks. All right, so the density enters because this one has a scale, has a length scale, but once you take out the factor that is due to the density with the correct power law, then it's a pure number. That's the point. And so in the end, whatever correlation functions you're interested in look like this in the ground state. So so it becomes a sum of these coefficients, which you may view as a matrix, as a matrix. So this A you can view as a matrix that takes that change the basis, if you want, between the operators in the microscopic model and the ones in the field theory. So basically, what this does is that it changes to the right basis in which the correlation functions behave in a nice way. And so you get okay, so you get a bunch of factors here, one for each operator, times correlation functions in the effective field theory, and the correlation functions in the effective field theory, you know them. That's the point. You know them because you can express them in the form that we did last Friday. And so basically at this point it's everything is solved. So I won't go into details. I mean, okay, if you're really interested in the actual calculation, it's in the notes. There is really not much left to do at this point. Basically, we have identified the correct geometry. It's this strip. We have identified the correct boundary conditions. We have identified essentially everything. And so you get the result for free at this stage, provided you have the correct coefficients here, these A's. And this is what was done by the fact that those coefficients are known for the Tonks-Girardot gas is really the result of a lot of work in mathematics and mathematical physics from the 60s and 70s. And so, as far as I know, the first to actually write the result were Tracy and Vaidia. And this is the one particle density matrix. So it is the correlation function of the boson distance x. So this is exactly what Thierry was talking about. And you see that here they have identified. So this goes as 1 over distance to the 1/2, exactly what Thierry was writing. Then they have cosine of 2x because they are using units in which the Fermi momentum is 1, and they identify the correct constant, the prefactor here, exactly. And this is it's using some results about Toeplitz determinants and Fisher-Hartwig conjecture and so on. So it's rather advanced mathematics, but the coefficients are known. And you see that the expansion that they get is precisely the expansion predicted by Lottinger liquid theory. They also have the short distance expansion, notice, and the short distance expansion, so this is for x very small, and at short distances it has the behavior I talked about earlier when I talked about Tan's contact, because the third derivative of rho has a non-analyticity here. So let me just zoom in on these equations. So this is the expansion. This is the constant. This constant prefactor. This is the short distance behavior. So at this point, basically everything is known, because the prefactors we know from them. And the technology to calculate the correlation functions, we have some from Lottinger liquid theory, and so yeah, that's it.